Now we will consider the fiber bend loss. Fiber bending means if we bend the fiber in this way, then we have a different type of loss that is called the bend loss. So optical fibers suffer radiation losses at bends or curves on their paths. This is due to the energy in the evanescent field at the bend exceeding the velocity of light right here, exceeding the velocity of light in the cladding, and hence the guidance mechanism is inhibited, which causes light energy to be radiated from the fiber. So basically this portion is actually radiated uh, through the cladding. The part of the mode which is on the outside of the bend is required to travel faster than that on the inside, so that the wavefront perpendicular to the direction of propagation is maintained. Hence, part of the mode in the cladding needs to travel faster than the velocity of light in the inside the medium. As this is not possible, the energy associated with this part of the mode is lost through radiation. The loss can generally be represented by a radiation attenuation coefficient of this form, alpha r equal to c1 e to the power minus c2 into r, where r is the radius of curvature. So this is the radius of curvature of the bending, and c1 c2 are the constants. So basically this particular kind of attenuation or loss is entirely dependent on the amount of bending, right? Amount of bending, and c1 c2 are just constant. It is dependent on other factors. Large bending losses tend to occur in multimode fibers at the critical radius of curvature of RC, which may be estimated. RC is nearly equal to 3 n1 square lambda divided by 4 pi n1 square minus n2 square to the power 3 by 2. So potential macro bending losses may be reduced by designing fibers with large relative refractive index differences, operating at shortest possible wavelength. So these are the way out. The critical radius of curvature for a single mode fiber written as RCS can be estimated as 20 lambda divided by n1 minus n2 to the power 3 by 2 into 2.748 minus 0.996 lambda by lambda c whole to the power minus 3, where lambda c is the cutoff wavelength for the single mode fiber. So actually these are called the micro bends because the radius of curvature is very small, this type of losses. So we have some imperfection in fabrication, so these micro bends occur. Hence, for a specific single mode fiber, that is a fixed relative index difference and cutoff wavelength, the critical wavelength of the radiated light becomes progressively shorter as the bend radius is decreased. Now, using this kind of mechanism, we can determine the amount of bending loss. Now, optical power escape from tightly bent fibers. Bending loss increases at lower wavelengths. So typical losses in 3 loop of standard 9 mm single mode fiber, that is 2.6 dB at 1310 nanometer and 23.6 dB at 1550 nanometer for r equal to 1.15 centimeter, that is bending radius or radius of curvature, and for 1.8 centimeter radius of curvature the corresponding losses are like this: 0.1 dB at 1310 nanometer and 2.6 dB at 1550 nanometer. So you can see how it is changing with the radius of curvature. Progressively tighter bend produce higher losses. Bend loss in insensitive fibers have been developed and now are recommended. Obviously, you have to consider the cost. Improper routing of fibers and incorrect storage of stack fiber can result in violation of bend radius rules. So as I said, this type of arrangement may be uh, is done to measure the bending loss. So you have number of loops and you measure the amount of optical power, and from that you can calculate the uh, amount of loss due to a single loop, and from that you can calculate the bending loss. So let us have a problem, numerical problem. Two step index fibers exhibit the following parameters. A multimode fiber with a core refractive index of 1.5, a relative refractive index difference of 3%, and an operating wavelength of 0.82 micrometer. And question B is an 8 micrometer core diameter single mode fiber with a core refractive index same as this one, a relative refractive index difference of 0.3%, and an operating wavelength of 1.55 micrometer. Estimate the critical radius of curvature at which large bending losses occur in both cases. So here delta equal to, as described in earlier uh, lectures, it is n1 square minus n2 square by twice n1 square. So we can determine the n2 because other parameters are given. It is 2.115. So RC approximately we have shown it in the previous slide. So if you put all the values, you will get 9 micrometer. RC is the 9 micrometer. For this fiber, single mode fiber, N2 becomes, using the similar process, N2 becomes 2.237, and the cutoff wavelength for the single mode fiber can be estimated using this relation. It becomes 1.214 micrometer, this one, and using this relation of RCS is nearly equal to 34 millimeter. So here we have 9 micrometer, here we have 34 millimeter.